In addition to naming molecules, which is really a way of getting at pattern recognition, another significant objective of each section of organic chemistry is to determine the chemical and physical properties of each class of molecules. Chemical properties are essentially the reactions each group can perform. These follow rules that are a little bit too deep into the weeds for the scope of this class, so we'll talk about each reaction specifically to understand it. The physical properties that we'll deal with, on the other hand, relate to intermolecular forces between molecules, which fall into four main categories. The total strength of these intermolecular forces will determine physical properties like boiling point and melting point, while the average strength of these intermolecular forces will determine to what extent a molecule is soluble in any solvent. The more similar the average intermolecular forces are between solvent and any molecule, the more soluble that molecule would be. The image shown here is cooking oil, which is mostly alkane in structure, and water, which are not able to mix because their intermolecular forces are not similar. We have four main categories of intermolecular forces, which will always be true no matter what molecule we're looking at. Intermolecular forces are the forces between molecules, not within a molecule. The forces that hold atoms together within a molecule, covalent bonds, are generally much stronger than the forces that hold two or more molecules together, the intermolecular forces. Between particles and molecules, the strongest forces are ionic forces. Ionic forces occur when molecules have at least a full positive or a full negative charge. The higher the charge, the stronger these interactions are. That means that ionic compounds are likely to be solid at room temperature. Think salt or sodium chloride. The ions are held together really tightly by these strong interactions, which means that it takes much more energy than is available at room temperature to start to get them to move around and become liquid. Ions that have a +1 and minus charge tend to still be similar enough in intermolecular forces to water that they're still fairly soluble. But ions with higher charges have interactions that are actually too strong for water and aren't soluble, like calcium carbonate, limestone. Most organic ions that we deal with have only a +1 or a -1 charge, and so small organic ions tend to be fairly soluble. The next strongest intermolecular force is intermolecular hydrogen bonds. The intermolecular is really important here. This type of force only occurs when hydrogens can be shared between molecules. It's not talking about like a carbon bound to a hydrogen, for example. This happens when hydrogens are attached to electronegative atoms, and there are available lone pairs to interact with these hydrogens on a different molecule. So this typically happens in organic chemistry only when there are either OH groups or NH groups, and the OH groups are significantly stronger for hydrogen bonding. Since water is all OH interactions, this is by far the most important force in water. And since our bodies are about 2/3 water, we care a lot about what can dissolve in water. Things dominated by intermolecular hydrogen bonding are clearly similar to water and tend to be pretty soluble. Dipoles, the next force, are present in almost everything that has a capability to hydrogen bond, but they're significantly weaker. We really only consider them if there is not an intermolecular hydrogen bond that's present. Dipoles get more complete coverage when you talk about molecular geometries in general chemistry, but they tend to be strongest in organic chemistry when there are carbon-oxygens that are double bound and relatively weak with carbon-oxygen single bonds, and then even weaker with carbon-nitrogen single bonds. Besides that, dipoles tend to be negligible in most naturally occurring organic molecules. The weakest intermolecular forces are London dispersion forces, which we call London forces for short. These forces are present in all molecules, but are so incredibly weak compared to the other forces that we ignore them except when they are the only force in a region of a molecule. London forces become important in stretches of molecules that are mostly carbons without nitrogens or oxygens, and of course in molecules with only one carbon. Because these interactions are so weak, they tend to hold molecules together poorly, and molecules with these types of forces only tend to be gases already or have very low boiling points. These weak forces are not similar at all to water's hydrogen bonding, and so molecules dominated by London forces are typically not very soluble in water. Even though these forces are weak, they often add up over larger molecules. This increases the boiling point, which you've probably already observed. Methane, or natural gas, is a single carbon alkane and is gas at room temperature, where butane, the alkane in a lighter, is liquid at room temperature. Type 4 plastic, the plastic in milk jugs, is essentially a very, very long alkane, and it's solid because there are more carbons to interact with each other. This works the other direction for solubility, though. Molecules with very long chains of carbons become less and less similar to water. Alkanes have only London forces, since they only have carbon-carbon bonds. This means they tend to have relatively low boiling points. This graph shows the boiling points of alkanes with 6 to 10 total carbons with various types of branching. There are 4 different patterns represented in this graph, but notice that every one of them starts with boiling points much lower than water at 6 carbons, but they still increase as the number of carbons increase. Every one of these data sets crosses 100 degrees Celsius between 7 and 8 carbons, which means that it takes us 7 to 8 carbons to get the same total strength of interaction from London forces that we got from the intermolecular hydrogen bonding in just the 3 atoms of water. Again, we see that London forces are much weaker, but they do add up as the number of carbons increase. Now I want you to compare the green set of points, which represents the normal unbranched alkanes, the straight ones, with a red set of points, which represents the alkanes with a methyl group at the second carbon. Are the boiling points higher for unbranched, the green ones, or for branched alkanes, the red ones, with the same number of carbons? In every case, for every number of carbons, the green dot is significantly higher than the red dot, meaning the unbranched alkanes have higher boiling points. That also means they have stronger interactions. That's because unbranched alkanes can stack right next to each other, but branching prevents the alkanes from interacting as efficiently. There's something in between them. That makes the interactions weaker and their boiling points lower. With that in mind, look at the graph and identify whether 2-2 branching, indicated by the orange, or 2-3 branching is more disruptive to the intermolecular interactions. Since the 2,2 dimethyl branching has a significantly lower boiling point than any of the other branching patterns for each number of carbons, that indicates that the 2,2 dimethyl branching is the most disruptive to the intermolecular London forces. It creates a much lower boiling point, which means that it's much easier to separate those molecules. This difference in boiling points is the basis for the refining of crude oil by fractional distillation. Crude oil is boiled and then cooled in a condenser that removes components at different temperatures. The longest chains of carbons, like lubricating oil, wax, and asphalt, remain liquid at very high temperatures. As the temperatures cool, shorter and shorter chains start to become liquid until only very short chains of carbons remain as gas, like methane. Alkanes have 2 main reactions: combustion and radical halogenation. These define the chemical properties of alkanes. Since most organic molecules contain some portion that's alkane, these reactions are not limited to alkanes, but will be possible for every functional group that we talk about. That's actually really important for combustion because it reminds us of how much energy can be obtained by oxidizing any sort of hydrocarbon, whether it's a carbohydrate or a fatty acid or a protein, if we oxidize that with oxygen. This process is broken up into little bits in our bodies, but it accounts for almost all of the energy in our metabolism. So you should absolutely know the products of combustion. The good news is combustion is easy to recognize and the products are always the same. Combustion in this class will always be some sort of hydrocarbon, so carbon, hydrogen, maybe some oxygen or nitrogen, combining with oxygen, O2. This is the only reaction with the O2, oxygen, that we'll see in this class. So if we see O2, we should think combustion. In this class, we're going to assume that there's always enough oxygen, and so the products are just going to be carbon dioxide and water. In reality, sometimes oxygen is insufficient for these reactions, and toxic carbon monoxide is produced instead, which is why you should always have a carbon monoxide detector if you have any gas or wood burning appliances in your home. You should absolutely recognize that O2 combining with any organic carbon source in some heat will burn to make carbon dioxide and water. That's the big thing that I want you to see with combustion. Carbons plus O2 gives carbon dioxide and water. Radical halogenation is a different process. We take a molecular halogen, so like Br2 or Cl2, in the presence of heat or light, and uses it to replace a hydrogen on an organic molecule, a hydrocarbon. Heat is often written as the Greek letter delta, the first one that's shown over the arrow, which looks like a triangle, while light is often indicated with an H for Planck's constant and the Greek letter nu, which looks kind of like a V. H times nu is the formula for energy from light. While this is possible on any hydrocarbon, it's really difficult to control, and it's used in practice only on very simple molecules. This can happen with any halogen, but chlorine and bromine are the most common and actually give us different types of products. Earlier, we talked about classifying carbon atoms as primary, secondary, tertiary, or quaternary. Quaternary carbons don't have any hydrogens that can be replaced and so aren't reactive by radical halogenation. We see different reactivity for the other carbons depending on which halogen we use. Radical brominations, which use Br2, are very selective. They will prefer to replace hydrogens on tertiary carbons with bromine when available, and prefer secondary hydrogens over primary hydrogens. There will always be a mixture of products, but the mixture will favor bromines on those more substituted carbons, that is, carbons attached to more other carbons. Radical chlorinations are not very selective. The more substituted products are always more stable, but radical chlorinations happen so fast that they'll pull off whatever hydrogens they can find. Since primary carbons often have more hydrogens available, we tend to see much more chlorination on primary carbons, although we again see a mixture of products. Practically, we might show a reaction like this. I'm showing conditions for a radical bromination. The Br2 written on the top of the reaction arrow indicates the presence of bromine as one condition, and the H nu, again, nu is the Greek letter that looks kind of like a V, indicates energy from light. This could just as well be heat, and both would give us the same types of products. To determine what the products would look like, we have to identify the hydrogens that are on this molecule first. Remember, there are always 4 bonds to a neutrally charged carbon, so each of the outside carbons that have only 1 bond shown actually have 3 hydrogens, and that center carbon only has 1 hydrogen. For bromination, that tertiary carbon, the center carbon, is preferred over the primary carbons. One product will then just have that hydrogen replaced by bromine. So we swap out the hydrogen that's on the center carbon for bromine. We say that this is the major product because it makes up the highest percentage of the product organic molecules. Those are the ones that we concern about. We also get some product where a hydrogen from an outside carbon is replaced with bromine. Each of the outside carbons is the same as the other, so they all give the same second product, which we call a minor product. Notice that we didn't write the HBr, which is also formed in this reaction. The HBr is considered a byproduct, a product of the reaction that isn't our goal but is necessarily produced. We often leave these out in this class, but there's no harm putting it in if you want. With radical chlorination of the same molecule, we get a different mix of products. In this example, I used heat to give the energy for the reaction, but I could have also used light, just as in the radical bromination. Chlorine will not react as preferentially to one type of carbon. So in this case, since we have 9 hydrogens that could be pulled off to give us the same product, our major product has the chlorine on a primary carbon, and our tertiary chloride is the minor product. Now it's your turn to practice a few. See if you can draw and name the products of these radical halogenation reactions. I wrote the reaction conditions a few different ways to emphasize that it doesn't matter whether we use heat or light, and that it doesn't matter whether the halogen is written before the arrow, like a separate reagent, or above the arrow as a reaction condition. Pause and try to work out both the major and minor products of each of these reactions. The first reaction is a radical bromination. There are 2 hydrogens on the central carbon, which is secondary. Replacing each of these, or either one of these, gives us the major product of bromination, a 2-bromopropane. 1-bromopropane is created when the primary hydrogen on either end is replaced by a bromine. Again, it's a minor product. If we take the same reactant, but with conditions for a radical chlorination, like is shown in the second row, the major product is actually flipped. It's the 1-chloropropane, and the minor product is 2-chloropropane. The third reaction is again conditions for a radical bromination. However, in this case, only one type of hydrogen exists, since the central carbon is attached to 4 carbons and no hydrogens. So the only product is 1-bromo-2,2-dimethylpropane as shown. For a final practice, try to predict the products of this reaction. A quick hint, notice that you're reacting with oxygen, not a halogen. Combining any hydrocarbon, regardless of structure, with oxygen and supplying sufficient heat will burn it and produce carbon dioxide and water. In general chemistry, you may have needed to balance this reaction. Here, I just want to make sure that you remember that hydrocarbons burn to make carbon dioxide and water. And that's it. You just made it through the longest chapter in our organic chemistry section. If you get the material in the last 3 lessons down really well, most of the remaining chapters of organic chemistry will only be slight additions to the nomenclature and our understanding of physical properties. Really only the chemical properties are drastically new from chapter to chapter. So take your time and make sure you understand this material really well, and it will really pay off.